All right. Well, thank you, Jens, for the very kind introduction. And I'd also like to thank Marcus for giving me the chance to speak to all of you here today. My talk is going to be on these two papers whose archive IDs I've included here. It's on considerations for implementations of LDPC codes. This work was done together with an amazing master's student who you should keep your eyes out for, Noiden Baspa, who is now currently going to Sydney to start his PhD with Stephen Bartlett. Before I start, let me say that this talk is dedicated to my late PhD supervisor, David Pilano. All right, so before I get started, let me get some boilerplate material out of the way, just to make sure that we're all on the same page. As I'm sure you're all aware, fault-tolerant quantum circuits are going to require some form of error correction at regular intervals. So as we construct a scalable circuit, we're going to have to interleave this with rounds of error correction. This is the content of some of the foundational results of the theory of fault tolerance, which tell us that scalable circuits will have to require some form of error correction. Now, not all error correcting codes are created equal. What is an error correcting code? First of all, it's some way for us to simulate a good qubit with noisy qubits, right? But not all error correcting codes are created equal. And so the question is, if I'd like to simulate some k logical qubits for the purpose of my algorithm, then how many qubits n, physical qubits n, noisy qubits n, will I require to perform the simulation? And the question is, can I get away with less? In other words, I'd like to maximize the rate k over n. I'd like to squeeze as much as possible out of the k qubits, out of the n physical qubits that I've got access to. The next concern is, of course, the distance. Which is a measure of how well these qubits are robust to errors. So if one of these qubits fails, then the simulation proceeds as is. But if too many of them fail, then the entire simulation goes off the rails. So we'd like to understand how much our code is able to tolerate errors. And there's always some trade-off involved in maximizing the rate and the distance simultaneously. Now, in addition to just using codes as a memory, we also need to manipulate information that's stored encoded in quantum codes, and this requires us to perform fault-tolerant gates. So if I were to perform operations on the physical qubits that I have access to, how would this in turn change the encoded logical information? And this is something that we would also like to understand. So these are some concerns that that help us pick an error correcting code. These are abstract because I haven't told you anything about the architecture. But in addition to these parameters that are sort of universal, there's also a question of how to perform error correction. Namely, I wonder why these points are not appearing here. Okay, great. How are your qubits arranged physically in your lab? And secondly, how many qubits are you going to measure simultaneously, right? So these joint measurements that are required for us to perform error correction are going to inform us whether or not the qubits that are in the support of these joint measurements either have an error or are error-free. And using this information, which I've indicated here using this check mark or this cross, we can then deduce whether or not there's some errors in the underlying physical system and how to correct them and return to the ideal code state. Okay. So today, the question that I'd like to focus on is inspired by the latter concerns, namely, how are our qubits arranged physically, and how many of these qubits am I going to measure at any given point in time? These codes are called low density parity check codes, and they're characterized by how syndrome information is gathered. So any given syndrome, in this case, so any given parity measurement that I perform to infer the state of my qubits only ever requires the measurement of some constant number of qubits, and every qubit only affects the status of a constant number of stabilizer generators. And these such codes are very promising for constructing scalable fault-tolerant circuits. They might simplify the process of extracting syndrome information. There was this very nice paper by Daniel Gottesman from 2014, where he showed that if you were to use such codes, then it might be possible for you, in contrast to the previous versions of the threshold theorem that I talked about, if you were to use an LDPC code instead of, say, a concatenated code as they've done before, the extra qubits that you need in order to perform a fully fault-tolerant quantum circuit might not be so much. And secondly, it's also been shown that these codes exhibit a threshold and exponential error suppression. So there's some error rate at which, if your gates are failing below this threshold error rate, then as I increase the block size of my code, there's this sort of wholesale effect that kicks in. And the probability for a logical failure decreases exponentially with the size of my code. And lastly, let me say that there is also efficient decoding algorithms that come with these codes. For now, we lack a complete theoretical understanding of these decoding algorithms. But the past few years, we've seen a lot of promising work. So this talk is divided into two parts. The first part is going to concern abstract constraints for constructing LDPC codes. And the second part is going to deal with physical constraints for constructing LDPC codes. Okay, so with the preamble out of the way, what is it that we're trying to do in theory space? Well, ideally, if I were to construct an LDPC code, I would like to ensure that it's local in D dimensions, where D is either 2 or 3. What does it mean for a code to be local? It means that any measurement that I perform only involves qubits that are in its immediate neighborhood. So another way for us to say this, if I were to consider a ball of radius W, then for any given stabilizer, there exists a ball of radius W around which all of the qubits that are being measured are contained. Okay. Unfortunately, there are some seminal results due to Brabi inter al. and later by Brabi-Poulin inter al. that tell us that locality is a very strong restriction for using quantum error correcting codes as a memory. By the way, if you have any questions, please feel free to interrupt me at any point. So the Brabi inter al result says that if I were to consider stabilizer codes, then the distance is capped. It's bounded away from growing linearly with a block size. And the second result is far more general. It applies to any code. It says that if the code is local, then there's a very sharp trade-off between the parameters K and D that we just talked about. By the way, if you haven't seen these bounds before, what do they mean in instances that you might be interested in? If we're working with two-dimensional codes, then the distance is upper bounded by the square root of n. The second bound says that the trade-off between K and D is as follows. It says KD squared can scale at most as n, right? So if you were to plug in this bound that you got from the Brabi-inter al bound, then you'd find that K has to grow at most as a constant. And the question is, how do we get around this problem? This seems to be an appropriate point to repeat Poulinism. We need to explore the space of all possible codes and understand what they're capable of doing, right? The surface code at this point has been explored a lot over the past 15 to 20 years. And when we do construct new codes, such as an LDPC code, it's difficult for it to compete on day one with another class of codes that's been explored for so long in such detail by an army of researchers. But we can't use this to justify getting stuck in a local minima in theory space. We should understand the space of all possible solutions to know that this, even if the surface code is the optimal construction, we should be able to convince ourselves that if we were to try other things, that they really do not work. Now, in order to optimize code parameters, people have been trying to understand what it is they can do to construct good quantum LDPC codes. Namely, how do I construct codes for which K and D can both scale linearly with N? It's easy to get around the first constraint. How do you ensure that K can scale linearly with N? There have existed codes for quite some time that get around this problem, namely the hypergraph product codes and the 2D hyperbolic codes are two examples of codes for which you can have a constant rate. On the other hand, it's less clear how to get around the distance constraint. And over the last year, the last half of 2020, we saw one breakthrough after another until December that culminated in this work by Pantelov and Kalachev, which demonstrated that you can get codes for which the distance is almost n. But the problem with these constructions is that as you increase the distance, you seem to sacrifice the code dimension a lot.
But this is also that encapsulates also the work by Ha and Hastings, right?
That's right. So these are their fiber bundle codes.
Yeah, in fact. Okay.
Right. So this is just to use as a setup. My point is that it may be indicating that even after we've given up on locality to construct these codes, there might still be some fundamental constraints that are preventing us from constructing good quantum LDPC codes. And so part of the motivation for this work, which we fell short of, but the motivation for this work is to try and see whether there exist constraints, even in the settings where we completely give up on locality, but there still exists some sharp KD trade-offs, a la Brabi, Poulan, et al. So I'll get to the concrete statement of that result shortly. But before doing so, let me talk about some other things that also motivated some results in this paper. So one way we'd like to manipulate encoded information that's stored in an LDPC code is to use something called a transversal gate. In its simplest form, what this means is that I'd like to perform some unitary operation U on every physical qubit, and I'd like that to translate to the encoded logical qubits. And the reason that these transversal constructions are so interesting is that if any one unitary fails, because they're all acting independently on these qubits, it means that only the qubit in the support of that unitary is going to fail. And it turns out that for information processing, in addition to just being a constraint for quantum memories, for information processing as well, locality is a very strong constraint. And there's this beautiful result by Bravi and Koenig, which says that if a code is local in D dimensions, then you're restricted in your ability to perform fault-tolerant gates. Now, I'm not going to state this in its most general form with the Clifford hierarchy, because that would take a little too much time in the introduction. And so let me state it in a simple form. Let's suppose that we want to perform the following diagonal rotation. This is a gate in the computational basis, which leaves the 0 state alone, and it adds a fine phase to the, it adds a fine rotation to your 1 state, and the angle, the fineness of this angle is dependent on this parameter m. The Bravi-Koenig result says that this angle is restricted by the dimension in which your code lives. And in particular, if d is equal to 2, then you're restricted to only being able to perform Clifford gates. There exists no short depth circuit that will allow you to perform T gates on the encoded information. There was then this very nice result by Pastowski and Yoshida, which showed that, in fact, there is a tighter form of this result, which says that in addition to the dimension and the fineness of this rotation, the distance also plays a very important role in dictating how well you can perform these gates. I'm not going to state this bound concretely just yet. I'll present it in a few slides when we present our bound, and it'll be used to contrast where we stand with respect to this bound. And so one might ask, there's been a lot of difficulty in extending these sorts of results to general LDPC codes. And so one might ask, maybe there's something deeper than locality that is the underlying problem. And on a personal note, let me just say that to this audience that together with Jens and Marcus, we've been trying to see whether it's possible, just like how we go from the Tor code to the hypergraph POTA code, we've been trying to see whether you can go from the hypergraph POTA code to a color code equivalent, which is able to support transversal gates, either Clifford gates or T gates. And this has been a very, very difficult problem. We've run into roadblocks every time we try and increase the rate for these codes. We find that a whole bunch of other things break down or is just technically infeasible. So perhaps, as I said to Marcus several months ago, perhaps this is hinting at some fundamental no-go result, and that's why we are unable to construct these codes. Again, we fall short of answering this question precisely, but we have made some headway. Okay, so with that out of the way, let me present some intuition and some of the language that we're using to state our results. As I'm sure most of you are aware, a quantum error correcting code is the joint +1 eigenspace of some set of commuting Pauli operators. And this is set to encode k qubits if the log of the dimension of this code space is equal to k. The logical operators are those that help you map from one encoded state to another. And this distance parameter that we're after is the minimum weight of an operator such that you can map from one state to another. At the heart of these results is the idea of a correctable region. And what does that mean? It means that if I were to consider some subset of qubits, then here, for instance, it's pictured using this blue, light blue blob. We would say that this blob is correctable if there exists a recovery map such that, so I have all of these qubits, this light blue blob has been deleted, but there exists some recovery operation such that I can act only on the qubits outside of this blob and return to my code state. Such a region is said to be a correctable region. And the fundamental insight from these papers by Brabi and Terhal, Brabi-Poulin and Terhal, and Brabi and Koenig is that the size and the number of these correctable regions in your error correcting code reveals a lot of information about the code. Namely, it tells you about the code dimension, it tells you about the distance, and it tells you about your ability to perform transversal gates. So being able to quantify the number of correctable regions in your code gives you a handle on all of these things and is a very powerful thing to know. Oh, there's a question in the chat. Oh, I see. Sorry. Well, I'll try to go faster. The one result that helps us structure that helps us understand what data structure that we need is builds on this result, on this notion of correctability. And it asks if I have two correctable regions, in this case, T and U, and if I know that T is correctable, and I know that U contains the qubits that are just outside of T, then in what cases can I envelop this entire region and declare that that entire thing is correctable? So this is called the union lemma. And it's possible to show that in some sense that if this is correctable and that is correctable and they share qubits in just the right way, then I can extend this set so that the whole region is correctable.
I'm sorry, may I interrupt? I'm confused. What's that symbol? That partial plus? That
it's just meant to denote the outer boundary of the set of qubits T,
okay.
meaning it contains the set of qubits such that they share a stabilizer with qubits in the interior of T.
Okay.
So I was just going to avoid that detail so that that's why I said they share qubits in the right way. Perhaps not relevant to get into the details at this point.
Okay.
Okay. So how does this affect our choice of data structure to represent our code? Well, we've got some set of qubits, and this structure is given to us as a graph. And I'd like to understand if this set B of R is already correctable, some ball of radius R, and I take one step and I envelop more qubits, then in what sense is the expanded object still going to remain correctable? And that is going to come down to understanding the connectivity properties of this graph, namely, when I go from the first ball to the second ball, how many extra qubits do I encompass? And the natural way to phrase this is in terms of something called a connectivity graph. So this is a many-to-one map. Here's an example using the surface code that will help illustrate this idea. So how does this example work? This is zooming in on some portion of our Tori code where this lattice is a pictorial representation of the code. There are qubits on the edges of this code, and the vertices and the faces of this lattice help us represent the stabilizers. Corresponding to every vertex, we have an operator that acts as X on all of the adjacent qubits, and corresponding to every face, we have an operator that acts as Z on all of the adjacent qubits. The map from this representation to a connectivity graph proceeds as follows. For every edge, or for every qubit in this case, I have a vertex in my connectivity graph. And between any two qubits, any two vertices, I draw an edge if they share a stabilizer. So this is some sort of clique complex that corresponds to the stabilizers in my group. Okay, so this is the object that we're going to be using to capture the connectivity of our general LDPC code. Now, how do I understand? So previously we said that at the heart of this result is this idea of bubbling out regions so that such that the union remains correctable. And to that end, we'd like to understand how to quantify the connectivity of this graph, right? And the way that we're going to do so is to use something called a balanced separator. Here's one way that I could phrase this. We're going to say that our graph is S separable if for every subgraph G prime that I consider. So here I've indicated the subgraph G prime using dashed lines. And let's say that the size of the subgraph is less than or equal to R. We're going to say that it is S separable if every subgraph has a separator of size at most S of R. Okay, so that was a mouthful. Let me just quickly repeat what I'm trying to do. The way that we quantify the connectivity of our LDPC code is using something called a separator, which is to ask, what is the minimum number of vertices that I need to remove to split the graph in two? And we would like to make sure that this is not just for the entire graph, that no one region of your graph is tightly connected or too tightly connected. So we'd like to say that regardless of which subgraph I consider, I'd like to have a handle on how well connected it is. And that's roughly what this statement is saying. It's saying that regardless of which subgraph that I consider, I'd like to ensure that at most I have to remove some S of R vertices to cleave the graph into two pieces, such that neither piece has too many vertices.
Okay. Sorry, perhaps you'll come to this, but how difficult is it to compute this quantity in general?
In exactly, you probably can't do it, but if you want to compute it approximately, then you can do it efficiently.
There must be some obvious connection to the graph theoretical dimension of this graph, right? Is this obvious, like what upper and lower bounds you have, like in the sense of the dimension that's defined by the growth constant of the graph, like the
growth constant of the graph? So I don't know the answer to this off the top of my head.
It's also a kind of a measure of connectedness if you want, but
right.
Okay.
Yeah, I don't have the answer to this off the top of my head, but perhaps Noiden does, and if you do, feel free to chime in.
Yeah, I can add something to this if you want.
Hi, you're online. Hey, welcome.
Yeah, I am. Thanks. Right. So if you have a graph of polynomial growth, so that scales out as R to the D, where R is your radius, and then you could embed this graph as a subgraph of the Euclidean lattice of dimension D log D. So that then gives you some guarantees on the separator of your graph.
Mm-hmm. Okay. Wonderful. Thanks.
All right. Yeah, so if anyone else has questions, please feel free to interrupt. Anyway, so we're going to say that an entire family is S-separable if every element of that family is S-separable. Okay. Yeah.
Sorry if I didn't catch it, but is R allowed to depend on S or the other way around?
R is just some parameter. So I say I'm going to fix some number R. S is itself a function.
Okay.
So here's an example that might help clear this up. So I fixed R to be some subset such that I can choose this subgraph. So it's a subset of size less than or equal to R. And what S is going to say is that if I were to consider such a subset of size less than or equal to R, then the size of the separator is at most S of R. So for example, in the case of a planar graph, in the case of the toric code, for any subset that I consider, I know that if I were to have, say, an L by L grid, I can remove the column of vertices from the middle and separate the graph in two. So it has a separator of roughly a square root of the number of vertices that you consider. Does that help?
Yeah, thanks.
So on the one hand here, we have these somewhat poorly connected graphs. These are planar graphs. And on the other hand, we have some very well connected graphs on the that are called expanders. And for such graphs, the size of the separator would scale roughly linearly with the size of the subgraph that you consider. So they're very tightly connected graphs. If you want to partition the graph in two, you're going to have to remove a lot of vertices. Okay. With this definition, it's possible for us to state our bounds. We're going to say that if we have a family of NKD quantum LDPC codes, and let's suppose that they have corresponding connectivity graphs G, then we're going to say that we're going to consider the particular case where the separator scales as R to the C. So it scales polynomially for some constant C. And the reason that we're doing this is because it's easier to present such a bound in a talk. What does this mean for the properties of our code? First, it says that the distance of your code can scale at most as n to the C. So the size of the distance is going to be upper bounded by the size of your separator. The second bound says that there's a trade-off between K and D that is induced by this separator. Namely that K is equal to D to the 2 times c minus 1 times n. What does this imply for our quest for constructing good quantum LDPC codes? Well, it means that, first of all, you can have constant relative minimum distance only when this S of R scales in proportion to R. Or in other words, if the graph contains an expander. Already this helps us understand what sort of structures we should be looking for.
Oh, wait, you lost me at this point. In that, yes, I understand that if you have an expander, then you get this specific scaling for the this separator. But how about the converse? I mean, you seem to indicate that the converse is also true, that you must have an expander of some type. Is this obvious, or have I not properly listened? Or
right. So this is only giving you an upper bound.
Yes.
Right. So if I tell you what this parameter c is, for example, with the toric code c equals 1/2, so for a planar graph c equals 1/2, then it tells you that the distance has to be upper bounded by square root n. So on the other hand, if I tell you that c equals 1, you're not guaranteed that the distance is going to saturate that bound. Okay. Right. So this is not a claim about existence. We don't know if these bounds can be saturated.
I see.
So
yeah. I mean, that was, of course, part of the point of our previous discussion is like to what extent one can even saturate these bounds. Okay, thanks.
Yeah.
That's a very good explanation. Thank you.
As a sanity check, we can go back and ask, how does this match up with the Rabi-Poulenc-Hall bound? If we were to consider a planar graph for which the size of the separator scales as a square root of r, then in that case, these bounds imply following restrictions on d and k. First, it says that the distance scales as the square root of n, and second, that k also must scale as the square root of n. If you were to compare this with the Rabi-Poulenc-Hall bound, which says that k times d squared is equal to n, it says something slightly tighter. It says that d is square root of n, but k is only a constant. So already there seems to be a gap between the BPT bound and this sanity check. Part of the reason for this is that planar graphs are not the only graphs with separators of size square root of r. You might have highly non-local graphs for which the separator also scales as square root of r. And it may be entirely possible for such codes to have a number of qubits that scales with the square root of the block size. So this is not clear. We don't know if these bounds can be saturated, but at least it only helps us provide a one-way statement. Okay. So for example, if you were to consider local graphs in 3D hyperbolic space, it turns out that these also have separators that scale only as the square root of the block size.
Hi, Annie. Okay, I lost track of a couple of things.
Sorry, yeah.
S, when you say separator, that's your little s.
That's right.
And what does that separator mean again? I missed that.
It just means that if I were to consider some subgraph of size r, then the size, the number of vertices that I need to remove to partition the graph into roughly equal size.
Okay. Yeah, sure. And that,
so in this case, is a function.
And that grows. Oh, I see. So it's kind of like, it's a bit like an area law, I guess.
Sure.
I mean, yeah, in 2D it's a one-dimensional line, and in 3D it's going to be a plane.
That's right.
So on, and then when you expand, it's going to be big. And R is just a constant, right? R is the number that tells you how many the support of your stabilizers, or like the support, how many, is that right?
No, R is a free parameter, right? It tells you, I would like to consider a subgraph of a certain size. So this blob might have, some size. It might have, I don't know, 10 vertices or something. And so I might say, what is S of 10?
Oh, okay, got it. Yeah.
So the point is just to say that if I were to consider that connectivity is not concentrated in any one portion of my graph, I can like move the subgraph around and still find that it's not like very tightly connected.
Okay. Oh, sorry, thanks.
You're welcome. Okay, so The other part of these bounds that applies to transversal gates also follows from this notion of a separator. So again, let's suppose that the separator scales polynomially, so as r to the c. And in particular, let's also assume that we have an LDPC code for which d scales as n to the alpha. So in this context, if you wanted to apply the following diagonal gate logically via transversal operations, then the following bound has to be true. It says that m is related to the distance as well as the separator via this bound. Now, if you're looking at it for the first time, of course, it's going to look funny. But just to help you get a handle on this, let me also provide the Pastowski-Yoshida bounds, but stated in this language. And so you can see that, as Ben pointed out, if you were to have a d-dimensional code, the size of the separator, the size of this constant c goes roughly as 1 minus 1 over d, right? So if you were to plug that into this bound, it would tell you that the angle of this rotation has to be bounded by 1 minus alpha over alpha times d. So if you were to compare these two, you can tell that the Pastowski-Yoshida bound is mostly better because it's tighter by this factor of alpha. But there exist certain cases in which it is possible for our bound to be very slightly tighter. So for example, if d equals 3 and you do happen to find a code for which the distance scales as n to the 0.6, then it turns out that you can only apply Clifford gates, whereas the Pastowski-Yoshida bounds tell you that you might be able to get away with T gates. And the reason for this difference is because of this extra +1 that sits in the Pastowski-Yoshida bound, but otherwise it's almost always tighter by this factor of alpha. So I'd like to thank the student here, Patrick Hayden's student, Sankri, for pointing this out. Okay, so as an application, we considered how our work might extend to classes of codes for which we didn't have a generic set of bounds. So for example, if one were to consider the class of hyperbolic codes in d dimensions, local hyperbolic codes in d dimensions, then there exists some very nice work by someone named whose last name is Kisfuluri-Bak, and they presented some bounds which gave you the separator for a d-dimensional local surface in hyperbolic space. So what's interesting is that once you consider d greater than or equal to 3, these bounds imply that the distance of a d-dimensional hyperbolic code has to scale as n to the 1 minus 1 over d minus 1. So you could compare this to the Bravi-Turhal bound, which said that a Euclidean code, the distance of a Euclidean code is capped by n to the 1 minus 1 over d. And so it feels like the distance, at least, is implying that the d-dimensional hyperbolic surface somewhat behaves like a Euclidean surface of 1 dimension less. And in addition, it also, these separator bounds also imply the following trade-off between k and d. And one can compare this to the Bravi-Poulan-Turhal bounds, and they look identical. This bound on the distance, however, seems to suggest that one might be able to encode more logical qubits in this case. So this is a generalization of the Bravi-Turhal bounds to hyperbolic surfaces.
But again, this is like a bound, right? I mean, it's not so clear to what extent this can be attained, but this suggests that there's some wiggle room to play with beyond what's in the Turhal paper, right?
Absolutely, absolutely. So just as the Bravi-Turhal bound itself, it's not clear whether or not you can saturate. So in the Bravi-Turhal bound, if you were to substitute d equals 3, it's not clear whether you can construct codes, local codes that achieve this bound, right? So we don't know.
Mm-hmm.
So we just want to highlight that these bounds don't apply to surfaces that you obtain by quotienting. So not hyperbolic manifolds, they really do have to just be local in d-dimensional hyperbolic space. When you quotient a surface, this could significantly change the size of the separator. So one might ask, when I do quotient to surface, is there anything that I could say? And previously there was this bound for surface codes and related codes by Nicolas Delfosse. It looks kind of like the Bravi-Torhall bound, except that it's Bravi-Poulin-Torhall bound, except that it's got this log K factor that it's modified by. We were able to borrow from results in graph theory that tell us how to extend such a result to surfaces of genus G. And here too, there's some very nice general bounds that apply to any code that's local on a surface of genus G. Okay, so with that said, let me move on to the second part of my talk, which concerns physical constraints for constructing LDPC codes.
Okay. Can I ask you one question here?
Yeah.
Yeah. So you're speaking of the separator, right? So
Yeah.
Would my guess be right that the length of the separator would basically be dependent on the locality of the stabilizer?
Right. So locality in what context, right? So when I consider an LDPC code, it's no longer local in D dimensions. When I give you an LDPC code, all I'm doing is specifying some connectivity graph for you.
Okay.
Does that help? So I'm just giving you an arbitrary graph, and I'm asking you what are the connectivity properties of this thing. There's no sense in which it's embedded in D dimensions anymore.
Okay. Okay.
Does that help?
Yeah, that clarifies.
So perhaps another question. So do these bounds like work well for all of these graph products that were introduced last year?
Not clear. You could even ask whether it applies to the. I mean, it always applies. The question is, if you can find a good separator, then yes, right? So it's if you can go away and say, I've computed this separator bound for this particular family of graphs, I don't know, fiber bundle code or something, then one might be able to then say, okay, what these bounds are tight or not tight.
But that's why it's not so easy to even compute these bounds, right? Because at the end of the day, it's not the property of the code as such or the graph, but rather finding good separators and then judging from these separators that you found, right? So in this sense, it might not be even obvious to what the bound is. Is that right?
You can compute the separator. You can compute the separator. Well, you can compute it approximately. So that might give you like a rough handle on how the distance and the KD trade-off will go, given an arbitrary family of graphs.
Fine.
But do you think, like, for instance, like in the case of the fiber bundle code, like you take two classical codes and then you apply like a twist at the end, do you think that the separator for these graph products would somehow depend upon these variable factors, for instance, the amount of twist in your base graph?
It could, I don't know. But even if we were to consider just a simple version of the hypergraph product code by Taylor Seymour from 2009, if you were to consider the product of two expander graphs, then the result is an expander graph, right? Whereas we do know that the distance only scales as the square root of n for such graphs.
I see.
So it's not clear whether that's because we weren't clever enough in coming up with a good construction of an expander graph that saturates the bound, or whether or not there's some more missing information that we haven't exploited.
But these separators, they only make sense as local quantities, don't they, Annie? I mean,
no,
you need
so for instance,
need to be a
if I were to
bullshit
consider an
region.
expander.
Well, I mean, local in the sense of that graph you made. Like
I could always consider an expander for, a separator for any graph. And in fact, the KD trade-off bounds, as well as the transversal gate bounds, they apply to any code and not just LDPC codes.
Yeah, what does local even mean in this context? I'm a bit confused.
Well, I mean, you could say locally with respect to that graph that you made at the beginning, right? You could say that, you know, you need a fully contained region, and then the boundary of this region are just the edges that go over the boundary of your region or something.
Right.
But yeah, okay,
But,
fine. Yeah, I agree. It's not locality is, yeah. What
that sense of neighborhood I could define for any graph, right? It doesn't need to be.
Yeah, that's what I mean by local.
Right.
I don't know, somehow like tried to minimize the number of edges cutting out through your,
Right.
okay, I don't know, I haven't thought very hard about it.
But I can express any code using a connectivity graph and then ask what are the connectivity properties of that graph.
Yeah, right, and some are better than others at telling you something good, I guess.
Right.
Okay.
All right. If there are no more questions, I'm going to proceed to the second part.
But maybe a follow-up question, sorry, because I didn't quite get it. I mean,
Yeah.
you can approximately compute these separators. I mean, the exact computation may be probably an NP hard problem or something. It's not, it's a combinatorial field. That said, you can approximately compute this. But what do you get for these like hypergraph product codes and like these different LDPC code constructions? Is this clear, obvious? Have you done this? Are these bounds expected to be good, or what?
Right. So for the case of the hypergraph product codes, if you were to consider product of expanders, you get an expander. So in that case, you might find that where was it? So for instance, in this case, can you see my mouse, by the way?
Mm-hmm.
Yeah. So you might be able to substitute C equals 1.
Yes.
So it might be a weak bound in that it tells you that D is equal to, or D is less than or equal to some constant times N.
Yes.
But that might not be the tightest bound, right? Because in the case of the hypergraph product code, I can exploit the structure of the code. I know a lot more about the code. And therefore, I might be able to say that there exists a much better bound. But that isn't to say that for all expander codes, this is true.
I see. Okay, fair enough. Thanks, that's great.
All right.
I don't know. I can imagine some like sensible definition of locality as being something like you pick bowl-shaped regions that minimize the number of, well, not bowl-shaped regions. I could define a bowl-shaped region in your expander space as being like, I don't know, with the fewest number of outgoing legs or something as a function of the number of vertices inside the region.
But then one has to be careful. That's not a tautology that you define it to be local when it's local somehow. I mean, yeah.
What? Okay, I mean, but my intuition says like those are the most useful regions you could make. If you could like, if you could minimize, you want to try and minimize the surface area of, some constant number of qubits that you pick in your region that I don't know, that may be disjoint or maybe not. You don't know in this picture, I guess.
Right. And so in some sense, the separator already captures this like minimization, right? So I'm saying across all subgraphs of size R, I'd like to pick a subset of vertices such that I can always guarantee that it can be cut in two using only S of R vertices.
Yes.
Sometimes I'm already like scanning over all of my code and asking, in the worst case scenario, what is like the most tightly connected set? And even in that worst case, I'm providing you a guarantee with S of R and saying it's not that tightly connected.
Hang on, so you want to maximize the size of the cut, not minimize it.
No, I want to minimize the size of the cut for any given instance, but I want to see in the worst case, how much can I minimize it? Right?
Okay, but then isn't it trivially minimal if you just take like a bunch of massively disjoint vertices, like
Right.
If I pick 3 vertices and none of them share any edges with any of them, then isn't the separator 0 and you just win? Okay. That's how this calculation works.
I'm not, yeah. That's right. If you consider disjoint graphs, it doesn't like buy you anything, right? Because in that case, this parameter C is just 0.
Yeah.
So I think once you picked your subset of vertices, you try to minimize the separator, but then you have to take the largest separator for all of your subgraphs.
Precisely.
Okay. Yeah, right. So you are trying to make. So I'm kind of
right.
saying my notion of what I think I was calling locality, but might need a better name.
Right.
Yeah, now I understand what you mean. That makes sense.
Is the maximization part of the minimization part. Yeah, okay, I get it. Like, sorry, thanks, Annie. I didn't mean to derail you too much.
And do you know how these algorithms that find the separator approximately work? Is it just okay? Easy.
So this actually reminds me of something Courtney was doing in his self-correcting paper where he was
Yeah,
taken the smallest cut through some fractal shapes.
Yeah,
Yeah,
so
so stat vector result for that.
Okay, yeah, let me return to that at the end of my talk. Okay. So yeah, we will talk about fractals at the end. Okay, so the second part of our talk involves how one could actually construct LDPC codes, say in 2 or 3 dimensions, right? So the bounds that we've had so far are just abstract bounds, and we'd like to understand what they mean for implementations. And as you remember, this story started with the Brabby-Turhal bounds and the Brabby-Poulan-Turhal bounds, which tell you that locality imposes severe constraints on the construction of codes. And of course, this then motivates the complementary questions, which is, suppose I have an LDPC code of code dimension k and distance d. How do I construct it, right? So how much non-locality is needed? And what do I mean by non-locality, right? There's this one obvious thing that you could do, which is to say, I'd like to quantify non-locality by the length of my edges, but is that all there is to it? And so to provide a little bit of intuition for why this is the case, consider the following example. Suppose I had a poorly connected code. So it's a very local code, and it has some connectivity graph G. And it's got some S, it is S separable, so S scales as little of n. So it's n to the C for some C less than 1. And I'd like to ask, is there some way for me to convert this mostly local code into a good code by adding some, I don't know, constant number of non-local edges? Maybe I can't add too many non-local connections. I'd like to add some very limited amount of long-range connectivity. Is there some way for me to promote this code to a good code? And unfortunately, the answer to this is no, right? Because this code would still have a poor separator, right? So if I added some edges augmented to get some graph G prime, then the size of the separator for my new graph is upper bounded trivially, because I could first tell you, remove the edges that you've added, the long range edges that you've added. And then underneath that, once I peel away these not too many non-local connections that you've added, underneath I reveal this poorly connected graph, right? So unless I add a significant number of augmented edges, I'm not going to change the size of my separator. So adding a little bit of non-locality is not going to change the properties of your code, regardless of how long these edges are. So the takeaway is that in addition to just the length of these edges, you're also going to have to be concerned with the number of these edges that you're adding. Okay, so this is how we're going to quantify non-locality. It's going to be both the length as well as the number of non-local connections that you need. So the second question that we'd also like to ask is whether or not there exists some way for us to implement a code in 2 or 3 dimensions such that a majority of your stabilizer measurements are spatially local. And what we're going to find is that there exists some bounds that say that some classes of codes are not going to be possible. I'll get to that shortly. So what is the intuition behind this second half? It's that a good quantum LDPC code, as we just discussed, requires a lot of connectivity. And in turn, this means that if a graph is tightly connected, the maximum distance between any 2 vertices is small. On the other hand, if I were to embed this graph in 2D or 3D, there's only so many other vertices that it can be close to. You can't pack in too many vertices. I'm restricting how much you can squeeze qubits into some area. So that forces you to have a certain number of long-range connections. So they're connected in the graph and they're close in the graph, but once you embed them in 2D, they have to be far away in real space. Okay, so somehow we're going to turn this into a theorem, and this is what is like an oversimplified way of capturing the intuition behind our result. Okay. So what are the bounds? They go as follows. Suppose I have an LDPC code as before and some connectivity graph G. We're interested in the following sorts of embeddings that map you from the vertices to the plane. And these are characterized by this parameter theta, which say that if I were to consider two qubits, then the distance between them is always at least theta, and I can't squeeze any two qubits closer than theta. So for instance, if you were to embed qubits in a lattice, this distance might, and in a unit lattice, this distance theta might just be 1. So if that is convenient, you can just set theta equals 1. And so our first bound tells us that if you were to have a code of distance d, then you're going to have to require at least d edges of length d over square root n. Okay, so let's try and parse that by plugging in various parameters of interest. So first of all, let's ask, how do I get past this constraint on 2D local codes? Let's suppose that I want to exceed square root of n distance. What if I exceed it by a little bit, so by some epsilon?
Sorry, but will you say more about the proof of this, or?
I am not going to get into the details of this proof now.
But it's purely high level, right? It's purely on the level of the graph itself, right? You're not going into the and using the bounds, but you're not using opening the hood and look at the codes itself or something. Or can you provide a bit of intuition how this goes?
Yeah, you're right. So I'm not really concerned with the exact code. I guess this is a very high level thing to say that if I were to provide you with a graph that has high connectivity, then that in turn is going to make it difficult to embed. And so in that sense, it's quite general. It doesn't really require that you understand any more about your code. Does that help?
It does perfectly help. That's what I hope to hear. Thank you.
Right. So if you want to exceed the distance bound of, say, Bravi-Interhall, even by a little bit, then immediately you find that the number of edges that you need, the number of long-range edges that you need, starts to grow. And furthermore, the length of these edges is going to scale as n to the epsilon, right? So there's this sort of threshold at epsilon equals 0, and as soon as you exceed it, immediately you start to have growing non-locality. And furthermore, we don't know if such codes exist, but if we could find codes for which d scales as n, then the length of these edges is going to scale as square root of n. And I think my diagram is in the wrong order, but let's just consider an example where suppose I had an L by L grid, as we did before. Then notice that square root of n is roughly the length of the side, and that any two vertices can be connected by an edge of length L, right? So in some sense, it's saying that if I were to have a code for which d scales as n, then I've got to use like the maximum amount of non-locality needed. Okay. Mm-hmm. Another way to state this would be to say that if you want local connectivity, right? If you want to ensure that the length of these edges is only a constant, then d cannot be greater than square root of n. Right? So it's a more general version of the Bravi-Interhall result. Our next bound can be presented in this in a simple manner as well. For the sake of reducing the overhead required to construct quantum codes, we'd like LDPC codes for which k scales linearly with n, namely constant rate codes, and for which d scales as n to the alpha for some parameter alpha. And our bound implies that for such codes, you're going to have some constant fraction of vertices in your connectivity graph that are connected to edges of length n to the alpha over 2. Right? So what does this mean? It means that there's a lot of non-locality. It means some constant fraction of vertices. You can't get away with a little bit of non-locality. You have to have a constant fraction of vertices that are connected to edges of growing length. Again, if you were to let d equals n, this would say that the length of the edges is square root of n. Okay. Right. So this bound also has consequences for Gottesman's construction. But both in the interest of time as well as not introducing too much more notation, let me pause here.
So those are upper bound. Sorry, Annie, can I ask you some more questions?
Please, please.
Those were upper bounds. Those little gray ones to the right hand side. The edges. I mean, can you prove that there exist codes where if you add edges of length n to the epsilon and n to the half plus epsilon of them, that you definitely get those codes, or is that a lower bound that they have to exist, or?
These are all lower bounds, right? So if you tell me, if you tell me I want a code with this k and this d, then you're going to have at least this many edges of certain.
They're lower bounds. All right, so that's for. I mean, okay, but then that's what BP got it. I see. Can you say then people don't really want to build 2D codes either? Does it make sense to apply these to 1D code or 1D lattices where you start with a distance 1 logical operator and try and make it a bit bigger and say, well, look, if you have a 1D array of qubits, then you can get a reasonably good distance on that low weight logical operator. Did you think about that, or do your results not apply it?
We have not.
I mean, if you're interested in practical results like that, people probably care a lot more about that.
Right. So in talking, I'm not sure if this is what you mean, but for example, Monica Schleyer-Smith's group here, they're interested in using a 1D array of atoms to construct a code. But
yeah, exactly. That's what I mean.
They're able to simulate long-range connectivity as long as it's periodic. So if, say,
it has to be periodic.
They said they were interested in translation invariant interactions in this 1D lattice, but that doesn't, at least so far, it doesn't seem to prevent you from constructing some expander graph with potentially, well, maybe not an expander, but some very high connectivity graph with periodic connections.
Yeah. Okay.
It's not clear to me what sorts of codes that you might be able to construct in 1D if you only had some translation invariant, but non-local connection.
Okay. Do you know things about the translation invariance of these things as well, or?
So are you suggesting that one could basically classify the translation variant settings, or?
I'm sorry, I didn't follow.
Are you basically saying that you could kind of classify all possible translation variant settings, or?
We don't say anything about translation invariance.
Yeah, that's what I thought.
A very general bound.
It's just a squared 2D lattice.
Okay, good, fine.
Yeah,
we're not. Yeah, it needn't even be a square lattice. All we need to understand is that any 2 points are separated by distance 1, right?
Oh, no,
So
no, I understand. For your general bounds, I was just interpreting the comment of Ben. Sorry.
Yeah. No, sorry, I mumble a lot, Jens. You'll have to.
Okay, good.
To repeat myself. Sorry, Annie. You should keep going because I'm asking a lot.
Annie, your results are not only for 2D, right? The ones that you showed here are. But
that's right. So they apply to D dimensions. The way that I've expressed them here is only for 2D. In general, you're going to have corrections that are also dependent on the dimension of your code.
I see. So that kind of embedding idea of your general results to like 2 and higher dimensions, that would work, as you say, in any other dimension as well.
That's right. So this factor, if I remember right, scales as n to the alpha over d.
Okay.
So sometimes 1 is special in these things, though, right? Like quite often results only work for 2 and up. But okay. I don't know exactly your method, so maybe 1 is fine.
I wouldn't be surprised if it worked for 1, but let me not make any claims that I don't understand.
Okay.
At least I can't think about live.
I think when you showed me the results, there was a D-1 somewhere because I thought about the same thing, but maybe it's.
Oh, yeah.
I don't. Yeah, I don't.
Oh yeah, that could be a 1 on D-1. I mean, Rabi Koenig doesn't make sense at D = 1, for example, right?
Right. Yeah. Okay. So for the last portion of my talk, I just want to quickly discuss how one could implement a quantum LDPC code using a a structure that's motivated by thinking about a concatenated code, right? So what would a concatenated code look like? Well, in the lowest layer, you have your physical qubits. And above that, you have like this self-similar replicating structure where you have one qubit that's composed of these physical qubits, and then an even bigger qubit that's composed of these like second layer qubits and so on. And the stabilizers for each layer are composed of operators that act on these lower layers. And so the weight of these things is increasing. Such a code would not be an LDPC code. But one thing that a concatenated model does inspire is that at the lowest level, the operators that you have to measure are still like local. And as you move up, you get more and more non-locality, right? So in this, what we're calling a stacked architecture, it's inspired by this model where you have several layers to your stabilizers. In your lowest layer, you have your qubits, and then what these sheets represent are stabilizers of some locality. The bottommost layer contains stabilizers that are entirely local. And as I move up, the radius of interaction of each of these stabilizers increases, but the number of such stabilizers decreases. Okay, so you have a similar sort of tree-like model where most of the stabilizers are entirely local and in the bottommost layer. But as you go up, there's a trade-off between locality and the number of stabilizers.
So it's a bit like in a mirror, right, where you also have a trade-off of numbers of vertices per layer and locality. So there should be an overall bound to the locality in actual numbers of vertices involved, right? For each layer, because I mean,
right.
There's fewer and fewer vertices, but at the same time, they're less and they're more and more non-local. But overall, there's a uniform bound to locality, right? If just counted in.
Sure, that is definitely one thing to do. So quantitatively, here's how the.
Oh, you say it. Okay, sorry. Okay. No, that's sorry. I anticipated this line. Okay, thank you.
So the topmost layer of stabilizers, they can talk to any given qubit. So it's like as non-local as can be, but there's only one stabilizer, some constant number of stabilizers that can do that. And we're not sure about the origin of this model. We know that David had been considering this a few years ago as one potential way to implement quantum LDPC codes. And more recently, Dan Gottesman had also mentioned this as one potential way to implement quantum LDPC codes, perhaps as a model for implementing the hypergraph product code or some of these other codes that we've been seeing. And it's not clear what sorts of codes that this stacked architecture will be able to implement, but it has too little non-locality to implement arbitrary LDPC codes. And what our bounds are able to show simply by these lower bounds that we had on the amount of non-locality that you needed, we're able to show that there is a strict bound on the distance of this code. So this is ignoring constants and log factors, but the distance scales as n to the 2/3. So almost like a 2D stack architecture behaves like a 3D local code in some sense, as far as we know. And then there also happens to be a trade-off between k, d, and n. So there's these exponents 3, 4, 5. So k cubed times d to the 4 is less than n to the 5. And unless your code, if your code violates either of these bounds, then it's not going to be possible for you to implement such a code using a stack architecture. So for example, these codes by Pantelev and Kalichev that were discovered late last year cannot be implemented using a stack because they violate the distance bound. On the other hand, it does not prevent you from, these bounds do not prevent you from implementing, say, a hypergraph product code using a stack, but there may be tighter bounds that do prevent you from doing so. Okay, but we are not aware of such bounds. But it was just good to see that this is like a general purpose bound, right? So previously, we were not sure what the capabilities of such an architecture might be, where a majority of stabilizers are local. And we can port our results to these general purpose bounds and say that regardless of what model you were thinking of implementing via stack architecture, there's some fundamental limitations on what you're capable of doing. Right. So, I'd be happy to discuss any questions that people might still have, and also future directions. But with that, I will conclude. Thank you.
Yeah, thanks for the wonderful talk. That was absolutely inspiring. We had lots of questions along the way. I'm sure there's more. Clap, clap.
Go on. I'm going to ask you a riddle question, Andy. Have you thought of any simple implementations for experimentalists?
No, actually, that's something that Noiten and I have been talking about. No, we're not sure. We don't know if there's some nice structures that, say, of an expander graph that might be able to, that you might be able to embed in 2D, where even though it's not, so what sort of structure can you make it have, right? Maybe you do require non-local connections, but maybe it's the sort where the 10th row is connected to the 15th row. So there's some like non-local connectivity, but it looks nice because it's periodic. So like along the entire row, like all of them get to talk between each other. So it's a sort of like rainbow structure. So would that be able to implement good codes? Not clear. It's not clear at all, but this is something we'd like to explore further.
Okay.
Can you do like an engineering? I mean, like, can you take your favorite expander graph and then construct a code from this? Like the Margulis expander is like a cute code, which is like defined natively on an n-by-n lattice, which is kind of translation invariant with this mix of nearby and a couple of like further away connections.
Right.
I mean, that seems like natively implementable with your stack structure. I mean, does this make sense to do a bit of reverse engineering of this type, or is that completely ill-fated?
No, that's a great idea. It's just we haven't considered it yet. So that's a great idea.
Okay.
So I saw a pretty cool talk before the world shut down at Squint at the start of 2020, and there was somebody at Maryland called Alicia Cola who was making hyperbolic geometries in circuit QED, where we could look at a hyperbolic code or something.
Right. I don't know this particular talk, but we have thought about a little bit trying to implement, say, 2D hyperbolic codes, like the quotiented ones, the hyperbolic manifolds in 2D. And there, at least, it wasn't clear how to draw these edges. It was terribly messy, and like I just went all over the place. So I don't know of a neat way.
Well, you're behind the experimentalist, Annie. Like, you should go look at the pictures in her papers. Yeah, they're making hyperbolic architectures on superconducting chips.
I'll take a look. Thank you.
Oh, yeah, you should.
Or if you look at PsiQuantum's papers, where they have very few, or they propose to start with very few resource state generators, but then have delay lines and connect them up in certain ways. That gives you very already a lot of structure on how connected you are. And then I bet your bounds will be very helpful to see how well can you even do with certain codes.
Yeah, that's right. That's another thing we have been thinking about. So asking, for instance, how does the length of the edges translate to, say, the time and delay lines or whatever, right? So
so that your bound would kind of provide insight to that effect, right?
Right. It translating between one language and the other would be helpful.
You can probably model the noise in an interesting way as well, right? Like if you have a photon that's got to go over, a length L, then
yeah, the
error rate of that photon is going to be proportional to L.
Oh, is it? I see. I didn't know that.
I think so. I mean, your photon's more likely to get lost over a longer cable, right? It's just
I see. I don't know how it scales as a function of the distance.
But don't you
I think
mostly
that's
get
true.
losses
I-
from putting the photon into the fiber and getting it back out?
Yeah,
Isn't that
that's what I thought as well.
So in principle it scales, but there's a huge constant factor in between.
Yeah,
That's a good point.
yeah, that's true.
I think that main argument is that like cables are very good memories. Like
Well,
not the
I-
bottleneck of the architecture they are envisioning.
I wonder if it's a good point or if it's a good sales pitch, Julia.
I don't know. They are the ones who want to build it, not me. Like
Yeah, that's what I mean.
Another question, so you mentioned this one project that you have with Marcus and Jens, and there you sort of alluded to the fact that perhaps there might be some other feature beyond connectivity that's constraining codes. Do you have any intuition for what that could be?
Part of the motivation behind that statement is to ask, why is there a gap between our bounds and the Bravi-Poulandra bounds or the Pastowski or Shida bounds? And the part of the reason that we are not able to get bounds as tight as theirs is because they're working with d-dimensional lattices. And why is that helpful is because when you cut a d-dimensional lattice and you consider this substructure, you're still left with a d-dimensional lattice, or maybe a d-1 dimensional lattice. So you have a very good handle on what the subgraphs look like and their connectivity properties. On the other hand here, all I'm telling you is that like at the first iteration, your separator has certain structure, and for every subgraph too, I know what the size of the separator is going to look like. But we don't have as strong constraints on the subgraphs that you get after you partition.
I see.
So if you were able to say something tighter, it's possible that you might be able to obtain tighter bounds, but that might not be as general.
Mm-hmm. I'm just sort of throwing this out in the air. Do you think that might just be a problem with the way you construct the code, i.e. by partitioning a d-dimensional lattice? And I mean, like, what if you went like the other way around instead of like, taking like two classical codes and then constructing your quantum code? Like, do you think like that might be a more efficient way to get bounds on the distance rather than like sort of partitioning from an established code?
The problem with any constructive approach is that it's constructive, right? Like, what if someone came up with a different thing tomorrow and they said, actually, you just weren't clever enough in coming up with a better construction. So you want to go top down rather than bottom up.
I see.
I mean, I guess that's kind of the problem. Like, for example, Bravi-Koenig was nice because the color codes were already saturating Bravi-Koenig, right? But we don't have nearly as many data points.
Yeah, I also wanted to say
LDPC codes to try and, like what should we be trying to saturate? They're just not enough good examples right now.
constructive,
even the
constructive approaches are great if you saturate all the bounds.
Yeah, exactly. Yeah, but I mean, BPT isn't very good after 3 dimensions, right? Or even after, 2 dimensions, it's saturated, but as Annie said in his talk, 3D is even not there.
If I can add something regarding saturating these bounds. So one potential explanation why these bounds seem hard to saturate is that I think they probably apply to subsystem codes too, whose gauge group has local generators. And in that case, these bounds would tend to be tight since they are known to be almost saturated for any d-dimensional space.
Hang on, d-dimensional, the code distance, d-dimensional. Oh, hang on, after the capital D. Yeah, that D. Yeah, sorry, I was a million miles away. Yeah, okay, right. So you think these are tighter for subsystem codes?
At least for the distance, yeah. Since there's that paper from Bacon, Slamia, Haro, and Chi, who pretty much saturate the distance bound for subsystem codes.
Yeah, that's right. Yeah, I forgot about that one.
What exactly is the intuition there? Like as to why
Regarding-
code, as to why subsystem code.
Excuse me.
I don't have that much intuition. The main advantage, obviously, of subsystem codes is that you can't remove problematic logical operators. My intuition is really limited to that.
I see.
Wonderful. So are there further questions? I must admit that I have to drop out rather soonish because I have to pick up my daughter from the shopping center.
Okay, thank you. Thank you for.
Annie, Marcus, shall we like set a date to kind of catch up in the next days a bit?
Sure.
And discuss more as you suggested.
Sure.
Like you are on Pacific time, right?
That's right. Yeah.
Which is a bit of a constraint. But overall, like 5 is not so bad. Or is that too early?
Well, I haven't woken up this early in ages.
Okay, sorry. Then I see. Okay.
Maybe we do this via email, right? Instead of in the recorded plenum. I mean, it's not like I have.
Yeah, I mean 6 is also fine for me. I mean, if I know this beforehand, I can arrange for that. I mean, the only days when I bring my daughter to bed, I'm constrained. Otherwise, I'm not constrained. Then 6 is also fine, or even 7.
Sure.
Good. Wonderful talk. That was super interesting.
Thank you.
So I mean, maybe as a kind of judging statement. So that's, I mean, in some way, this is like rather bad than good news, right? It does constrain the possible code constructions slightly more than anticipated, I would say. No, I mean, what's your, I mean, zooming out, what take home message of all this?
Well, we now have some way of quantifying how bad is.
Okay.
So if you know that in particular architectures, you're unable to engineer these sorts of interactions or this many long-range interactions, then you're out of luck. But if you're dealing with, I don't know, some silicon qubits mediated by photons, and you can get anything talking to anything else, then maybe that's not so much of a problem.
I see. Oh, no, indeed. I mean, yeah, of course. I mean, locality means something different for different architectures. I mean, that's clear.
Right.
I mean, for example, exactly. I mean, when you talk about psi-quantum type photonic things, I mean, then there's lots of problems all over the place, but locality is not so much the problem, right? I mean, that's the least of your worries, that you can let stuff talk.
Or it's an architecture dependent problem. So architecture versus locality, I guess. So it's just saying that if you have these problems with your architectures, then you cannot implement these sorts of codes, because if you have a target dimension and distance in mind, then you're going to have to require at least this many non-local edges, and you're out of luck.
Mm-hmm.
I guess nobody expected to make an LDPC code in some local number of dimensions. Anyway, it's nice that it's all counted.
No, indeed. I mean, of course.
Or bounded. Yeah.
So I guess some questions that we've been asked before was whether or not you could like catalyze the construction of an LDPC code, right? Like if you can start with a mostly local code, add not too many non-local edges, and then convert it to a good code. And already we know that that's not going to be possible. So there's no like middle ground. You have to add a lot of non-locality before you get there. So that's at least one concrete thing that's come out of this.
Yeah.
Also, I guess I mean like classical LDPC codes like expander type codes are not like locally embeddable in like R3 or R2, right?
They are not. That's right.
So I mean, like, why would anyone expect the quantum versions thereof to be locally embeddable?
It's less a question of expecting them to be locally embeddable, which is just saying, no, you can't, versus asking how bad is it? And what do you mean by not locally embeddable? Like how non-local is non-local, right? Like actually putting a number to it. Because anything from a 2D hyperbolic code, which has say distance scaling as log n, all the way to these fancy Pantelev-Kalichev codes are all non-local. But would they all be implementable the same way? Probably not. And depending on the parameters of your code, you're going to have to require different degrees of non-locality, and you'd like to put a number to that.
Mm-hmm.
If I can add something too, I think the quantification of non-locality in this context is kind of interesting because it allows you to discriminate between what different architectures will be able to do in the long run, in the sense that if you want, today controlling qubits is obviously very hard, right? So you want to be able to minimize your overhead. Ideally, you would like constant overhead. And the results we have that exists that can guarantee constant overhead rely on constant rate and polynomially scaling distance. And what we show is that basically some architectures will, to the best of our knowledge, are simply not able to implement this kind of schemes, right? So if you should try to think of what kind of architecture will be useful in the long term, yeah, it seems particularly relevant to consider whether you can implement a linear number of polynomially scaling long-range interactions, which is strongly not possible in some architectures.
Right. So for example, that reminded me, I've heard of some teams considering the following architecture where you have local codes, blocks of local codes that are going to talk to each other by some non-local connections, right? So you can ask, would that be sufficient to promote the entire thing to a good code? And you might ask, like, given that I have this limited amount of non-locality where it's like local patches connected by these things, is there some restriction on the best code parameters I can achieve for such an architecture?
Mm-hmm. I see.
And also, we've formulated these bounds focusing on the Euclidean space, but the advantage of having this graph theory framework and showing that if you have linear distance, then you have an expander. The advantage is that graph theory has a lot to say about expander graphs, obviously. And most notoriously, their radius grows very quickly. So the basic argument we use to prove the lower bounds on the distance and number of long-range interactions is that if the space in which you're trying to embed your code has bounded growth, then you're going to end up with these long-range interactions, which is interesting because it applies to any kind of matrix space you might want to consider. So potentially, I would be kind of interested to know if this has any kind of application in, for example, holography or these kind of stuffs.
Interesting. I mean, it's not inconceivable, right? Because I mean, like a tree is basically like an ADS space-time. If you think of curvature in terms of Schläfli symbols, then this kind of layered picture that was shown at the end, it has resembles in some ways like a kind of curved ADS-like geometry, right? If you really want to. So that might be worth thinking about.
Jens, I don't want to hold you up if you have to.
Yeah,
go.
no, that's fine. It's just too interesting. I mean, I'm torn between letting my daughter wait and learning more from you. But let me last question.
I'm happy to hang around here and chat after.
Yeah, I already made Marcus the host. So I mean, there's many expander graph constructions like the Margulis one I mentioned, but also of course random constructions. There's lots of probability measures according to which if you draw a random graph, then with probability 1 asymptotically, you get an expander graph. So is this a meaningful construction? I mean, it would be like a random construction if you think of such a construction combined with like this Hastings construction. Is this worth thinking about, or is this a crackpot idea?
Well, the core of the idea is good. That there might be constructions other than the Margulis one that are good. Random constructions don't have much structure you could exploit, but there exists, say, the Lubotsky-Philipp-Sarnak one from '88, and also later product constructions, the zigzag product, which are used to construct expander graphs.
Mm-hmm.
And these might be very handy in understanding the sort of connectivity that emerges, because there's a lot more structure that you can exploit in order to construct the graph.
Mm-hmm. Okay.
So it's entirely possible that because of the LPS construction and the nice like group theoretic properties make it amenable to embedding. I don't know. I'm just spitballing here. I don't really know what it would imply.
Mm-hmm.
But there you do have structure that you could exploit. So it's conceivable that you might be able to work with that.
Okay. Thanks.
Especially since there's some interest in separators in metric group theory, which generated some tools to actually calculate the separators for some kinds of Cayley graphs, including some fractals. So yeah, that kind of tools can become quite versatile in this context, especially when you're trying to build quantum codes, which indeed require a lot of structure, and so you tend to use groups quite often.
Mm-hmm. Okay.
So I think one of the points that was brought up at some point, I think by Ben, was this Courtney-Brell construction on fractal codes. Do you have any thoughts there on how your Cayley graph results might apply? So because I remember, so what was it that, so you took the homological product of two quantum codes that were defined on a fractal surface, and in the end he got like a 4D fractal toric code. But I think the belief was that it might be possible to implement it in 3 dimensions. So using your construction, do you think it might be possible to say something definitive about a 4D fractal construction of that type?
Yeah, it's a good question. I don't know. It's not clear.
So a puzzle that Courtney left behind, which is why he didn't get all the fame that he was hoping for, is that his embedding theorem, getting it into 3 physical dimensions from 3 Hausdorff dimensions, wasn't. Yeah, something went wrong with it, so that part of it needs fixing as well. But that isn't to say that you could. I don't know if you. Presumably, you can't embed any of Annie's codes. Well, no, he didn't make LDPC. He didn't do. He is good. So he didn't invent LDPC codes. I don't think that's mean.